So last time we were talking about mechanisms in substitution reactions, right? And we pretty much so finished off at this slide. But before we finish up that stuff, we had two mechanisms. What were they? SN2 and SN1. What distinguishes an SN1 reaction? It's two steps, right? SN1 is a two-step mechanism, right? Describe it for me. What are the two steps? Step one is what? Pardon? Okay, it is the rate determining step. What's happening in that rate determining step? Leaving group leaves, right? And so we end up with what as an intermediate? Carbocation intermediate. Is that stable or unstable? That's right, it's unstable, so it's high energy, right? What's the second step? Nucleophile attacks the carbocation. That's right. Okay? SN2 reactions are how many steps? Okay? And how are they distinguished? Tell me how that happens. Okay, so the nucleophile comes in from the back at exactly what?
Exactly the same time as the...
Okay, so as it's coming in, the leaving group is leaving, 180 degrees, right? What's the rate equation for an SN2? Second order, so rate is equal to K times the electrophile times the nucleophile, right? Okay, so what's the rate equation for an SN1? Right, so rate is proportional to the K times the electrophile concentration. Nucleophile never comes into the rate equation at all in an SN1 reaction. So if you were doing an SN1 reaction and you came to the lab and you wanted to get to lunch real quick, so you wanted to speed it up, and you started adding more nucleophile, you're going to be there just as long. It doesn't matter. It doesn't come into the rate. If you wanted to speed the reaction up so you could go to lunch early, you want to increase the electrophile concentration, okay? Now, if you were doing an SN2 reaction and you wanted to get done early, I would suggest you double both things, right? Because if I double the electrophile and the nucleophile, what happens to my overall rate? It quadruples, right? So that's a good thing. And we also started talking about the fact that these nucleophilic reactions are actually useful in biology, right? So somebody describe for me what's going on here and why this is important for you in biology. You're making adrenaline. Why is that important? Okay, so we live in that
state all the time, but you need that state at certain times.
Yeah. And what else? What kind of reaction is it? Is it SN1? And how do I know it's SN2? We're going to learn more about that today. But based on what you see there, how do I know that that's an SN2 reaction? Notice the number of arrows I have, right? I show the nucleophile attacking the carbon, and I show the leaving group leaving all at the same time. Okay? So this is the equivalent, SAM is the equivalent of iodomethane in biology. But you can't have iodomethane floating around in your body. But you can have SAM. Okay? So all that nucleotide stuff that's on there, nature just uses that for a couple of reasons. But primarily, it's a great way to make a leaving group. Okay? And it works. So SAM costs about, if I remember right, if you were to buy a mole of SAM, it's about $200,000. Or I can go into the laboratory and buy a mole of iodomethane for about $60. So what am I going to use in the lab? I'm going to use iodomethane. But your body can't use iodomethane. Number one, it's not water soluble. SAM is. Okay, but if you were to buy pure SAM, based on Aldrich prices, it's over $200,000 a mole. So don't come into my lab and say you want a bottle of SAM to do a simple reaction like this, because it's not possible financially. All right, so the SN1 mechanism, two features, right? You got the slow step, which is the leaving group leaving. We get the carbocation. Tell me something about the geometry as we go from alkyl halide to carbocation intermediate. All right, we go from tetrahedral to trigonal planar. What happens to the hybridization of that carbon? Okay, we go from sp3 to sp2, and it's trigonal planar. So if I had a model of that carbocation, could you distinguish the top from the bottom? No, they look identical. And so if you're a nucleophile, what are your odds of attacking from the top or the bottom? Equal, 50-50, okay? 1 to 1. I don't care which ratio you use. Okay, equal, 50-50, 1 to 1, it's the same thing. So when I have a planar carbocation, the top and the bottom are identical, okay? Now we have this second step where the nucleophile comes in and reacts at the carbocation. That is a very fast step. It's completely downhill energetically because we're forming bonds, right? And we end up with our product. So overall, what did we do to the alkyl halide here? We took the alkyl halide, we reacted it with acetate nucleophile, and what did we get? What's the product? It's an ester, right? So you all should be seeing right now that alkyl halides can be converted into a lot of different functional groups. We've converted alkyl halides into alcohols. We just converted an alkyl halide into an ester. We've converted alkyl halides into azides. We've converted alkyl halides into nitriles. We've converted alkyl halides into thiols. You can do a lot with alkyl halides. This is a hint that you're going to have to do an awful lot with alkyl halides. So it's something that you really need to commit to memory. Okay? If we were to look at the energy diagram of this particular reaction, it would look something like this. And we can clearly see why this first step has to be the rate determining step. This is the tallest mountain that we have to climb, right? Right here we are at the transition state where we're breaking this bond, right? We're starting to look like a carbocation, and here we are at a carbocation in this well. We call this an intermediate, okay? So we can detect it. It does exist, but it has a very fleeting lifetime because the second energy of activation is relatively small comparatively, and so it goes on to product quite quickly. The concentration at any given moment of carbocation is pretty close to 0. It's not exactly 0, but it's really small, okay? Because as soon as it forms, it wants to react, okay? So the transition state for this reaction, if we were to talk about the hybridization of this carbon, or the geometry, let's say, of this carbon, would it be more similar to the starting material or more similar to the carbocation intermediate? And why? That's right. And whose postulate is that? That's Hammond's postulate. That's exactly right. So the transition state is going to look more like the species, which it is closer to in energy. And if I look at this, it's a lot closer in energy to the carbocation than it is to the energy of the starting material. Okay? And so we know something, even though we can't directly detect transition states very easily, the fact that we can detect a carbocation and the fact that we know that it has to be close in energy, we can kind of start to guess what that transition state looks like. We can get good ideas of what that transition state looks like. Okay? So if we look at a carbocation, right, we have a trigonal planar carbon atom. We have a vacant p orbital. What are the two colors for? Down and up what? Okay, one's above the plane, one's below the plane. It has to do with the sign, right? So you go from, let's say this is positive, because there's a plus sign in there, although it's a carbocation. You go through the node, you have to be at the negative sign, right? So plus and minus have to cancel out to give you 0. So that's why that we use two different colors here. You can use shading, you can use different colors, you can whatever you want, okay? But you do have to show the mathematical sign being different, okay, in terms of the wave function, because these are all wave functions, if you'll recall from way back when. Okay? So let's do an experiment. Let's suppose we start off with a chiral alkyl bromide. Will everybody agree that this is chiral? Okay, we've got a bromine, we've got a methyl group, we've got a deuteromethyl group, and we've got an ethyl group. So we've got 4 different things around this carbon, right? And if I look at it, what would you say? That would be the lowest priority group, right? And it looks like it's going 1, 2, 3, so it's really what? If it looks like it's going this way, it must be going the other way, right? So it's really S. The leaving group leaves. We become planar. What happened to our chirality? It's gone. Now wait a second, I still have 4 things around that carbon. I've got a p orbital, I've got a methyl group, I've got a deuteromethyl group, and I've got an ethyl group. But why did I lose the chirality? Huh? P orbital's a thing. It's a thing. It's not a bond, that's true. So why is it not chiral? What does it have that chiral things cannot have? What kind of symmetry? It's got, yeah, you got a mirror plane that runs through it, right? And so if you had this in your hand, you would see that there would be a mirror plane that goes through the node of that p orbital. Okay? And so we cannot have chirality at this point because it's planar and it has symmetry, right? And so now the nucleophile can either attack from the, let's say, the right side or from the left side. If it attacks from the left side, we end up with this molecule. I think you all will agree that that's chiral, right? If it attacks from the right side, we end up with this molecule, which I think you will agree is chiral. How are these related to one another? No, they don't rearrange. How are they? Oh, they're non-superimposable mirror images, right? So they are enantiomers, right? So I have a molecule right now that rotates plane polarized light, and my products do what? They won't at all. So if I had Harry come in and run this experiment with that little polarimeter, we would start off by seeing a rotation of plane polarized light, and as the reaction proceed, it would get closer and closer to 0 until finally the reaction is complete and it wouldn't rotate plane polarized light anymore. Okay? And so the reason is because we know we have to get a 50-50 mix because the odds of attack from the left or the right is identical. And so we're going to end up with a racemic mixture where we have a 1-to-1 mixture of enantiomers in my products. Okay? So let's do this particular experiment in our mind anyway. Okay? So we start off with R minus 2-bromo-octane, chiral molecule, right? And we place it in water, and we're going to do what's known as a solvolysis reaction. What does that term mean? What'd you get from your reading in terms of solvolysis? That is where the solvent is also a reactant, in this case a nucleophile. That's right. Water can function as a nucleophile. So we're going to take this alkyl bromide and we're going to convert it into 2 alcohols. Now wait a second. If this is an SN1 reaction, what should my products be? No, those are intermediates. We will have an intermediate. But what would my products be if it was SN1 that we've talked about so far? No. You're overthinking it. What kind of mixture should I get? Racemic mixture. Do I have a racemic mixture? How do I know it's not racemic? It's 83 to 17. So does that suggest that this might be SN2? SN2 must be what in terms of the chirality? If we start off with R, we must get S completely. Complete inversion of stereochemistry defines an SN2 reaction. Oh boy, what do we have here? We don't have a racemic mixture, nor do we have a complete inversion. No SN3. Explain it to me. What did our previous mechanism assume in terms of generating the carbocation? All right. When we take off the bromine, we had a planar carbocation that had mirror symmetry, right? What did that assume about the bromide? Let's think about it. What does that assume about the bromide? Where is it at? In the intermediate. Do you see it anywhere? No. It has completely left and gotten completely out of the picture. In real life, that's not the way things actually work. It can, okay? But think about it. As that leaving group leaves, does it leave equally from both sides? No, it just leaves from the side that it's on, right? All right. So what happens is, as the bromide leaves, which is going to be our little orangish red, whatever that color is, sphere, we've got our planar carbocation, but notice that the leaving group's on one face. It's not connected anymore, but it's still dissociated. It's still near. Why is it near? Because we got a positive and a negative, right? It's not going to completely get the heck out of the way, right? Electrostatic attraction. My nucleophile is either negatively charged or has lone pairs. So if you want to attack from this side, is that going to be favorable? No, but attack from the top is going to be more favorable. And so you're going to end up with more than 50% and less than 50%. So SN1 can be complete racemization, but not usually. Usually you have partial inversion. Okay? Why partial inversion? Because the nucleophile has a greater probability of attacking this face, which leads to the inverted stereochemistry, because the leaving group's not on that side. Okay? So we've broken the bond, but now it's kind of like an ionic compound. Okay? It no longer has the covalent bond, but that leaving group hasn't just let me get out of the way, right? And so you're going to get more than 50% inversion, and you're going to get less than 50% what we call retention of stereochemistry, okay? Because of these electrostatic interactions. Does that make sense? Okay. Not all carbocations are equal in terms of stability. There are quote-unquote stable carbocations, and by that I do not mean that I can put them in a bottle and keep them for a month, okay? It's relative. And then there are carbocations that are so difficult to make, people actually got a Nobel Prize for proving that you could, okay? CH3 plus is one of them, okay? George Olah won a Nobel Prize for developing what are known as magic acids. I know, okay? But he was able to show a lot of carbocation chemistry that we thought impossible in these special acids, okay? So, that's for another day, okay? So, basically, methyl carbocation is very, very unstable. But a tertiary carbocation is quite stable, relatively speaking, to the others. So tertiary alkyl halides will undergo SN1 or SN2 chemistry. They undergo SN1 chemistry. What about methyl halides like iodomethane? SN2 chemistry. Primary carbocations are also difficult to generate. But secondary, you can do. So methyl alkyl halides and primary alkyl halides almost always do SN2 chemistry. Tertiary alkyl halides always do SN1 chemistry. Secondary is what you have to pay attention to, because secondary can do SN2 chemistry, but it can also do SN1 chemistry, and that's where you're going to get confused most of the time. Now, these figures that you're seeing in your book, okay, these are electrostatic potential maps that are generated using that software that I have, okay? Blue is bad, okay? Blue means you have a lot of positive charge, okay? Notice the methyl carbocation, pretty blue, right? What about for the tertiary carbocation? Barely blue. That means that the positive charge has been delocalized over the entire structure that we have here as shown, okay? And that means it's more stable. And the reason that it's more stable, the more alkyl groups we add to a carbocation, the more stable it becomes because of this term called hyperconjugation. Okay? So, if you look at a methyl carbocation, you see that the hydrogens are all in the plane of the node. These electrons that are in the carbon-hydrogen bond cannot populate at all the carbocation. However, when we start to add groups, alkyl groups, notice that these CH bonds can actually overlap with the methyl, or not with the methyl, but with the carbocation. Okay? They actually come into contact, and so some of the electron density in that bond can actually stabilize that carbocation. Now, in this case, we have two methyl groups. Only one of them is showing the hyperconjugation for clarity. Both of them are actually contributing to that. So the more alkyl groups I add to a carbocation, the more stable it's going to be. What else could I do to stabilize a carbocation? I can add alkyl groups. What else can I do? I could add a functional group. What kind of functional group might I add to stabilize a carbocation? Do we have any negatively charged functional groups? Oh, we got some lone pairs though, right? So if I've got a carbocation, so let's say that's my carbocation, right? I could add what to it? I'm just going to put R for anything. Yeah, those lone pairs could donate, and we could draw a resonance structure for that, right? That could stabilize a carbocation. What else could I do to stabilize a carbocation? Okay, so anything with a lone pair can do it. What else could I do? What about if I had this carbocation versus this carbocation? Which one is more stable? The one on the left or the one on the right? They're both primary, right? Not really. Why not? One of them has resonance. That's right. I can draw resonance structures. Right? What happens as I draw resonance structures? What happens to the stability? It increases. So I can generate stable carbocations by using heteroatoms. I can generate stable carbocations by adding more alkyl groups. I can generate stable carbocations by putting things that can draw resonance structures with, like alkenes, okay? And so it looks like this is primary because it's only bound to one other carbon, but it's to a special carbon that allows me to draw resonance structures. And so we call that an allylic carbocation. Little different term. So let's continue talking about some carbocation stability. As we mentioned earlier, right, SN1, we have the bond breaking followed by the bond making. So we have this carbocation intermediate. Anything that stabilizes that carbocation, what's it going to do to the rate of the reaction? Increase it or decrease it? If I stabilize the carbocation, you think it's going to decrease the rate of the reaction? Let's think about the energy diagram again. Right, there's my carbocation. This is my slow step, right? That's my RDS, my rate determining step. And you told me that this is going to look closer to this, right, in terms of how its structure? Okay? And you called that the Hammond postulate. You're absolutely correct with that. If I stabilize that, what's that do to my transition state? Brings it down, which does what? If I bring down... But if this is less stable, that means it would be higher in energy, right? That's not how it works. So think about it. If this structure, my transition state structure, is similar to this, as I stabilize that, it's also going to stabilize my transition state and bring that down. So the energy difference from where I start to where I end up is smaller. The smaller the energy of activation, the faster the rate. Okay, that's just your general kinetic theory, right? So if I stabilize my carbocation, I'm going to increase the rate of reaction, okay? And so anything that I can do to stabilize that carbocation should therefore increase the rate of the reaction, okay? And so that's what we see here. Methyl does not do SN1 chemistry, so the rate of reaction is essentially 0. Primary carbocations are very difficult to generate, so the rate of SN1 reaction there is essentially 0. Secondary carbocations, we can start to do SN1 chemistry, but it's going to occur a lot slower than a tertiary alkyl halide, okay? Because the tertiary alkyl halide can form a very stable carbocation, we're going to have a faster reaction rate. This trend is exactly the opposite of what you would expect for SN2. Tertiary alkyl halides do not do SN2 chemistry, but methyl alkyl halides do SN2 chemistry real quick. Can anybody explain to me why SN2 is exactly the opposite of SN1? What do you think, Sayer? I'll call you out. What's the difference? Let's start with the difference. What's the difference in an SN2 reaction versus an SN1 reaction? Has one step, very good, and it has what involved in that one step? Right, so we have the nucleophile and the electrophile involved in that rate determining step, right? So why would an alkyl halide that is primary or methyl, either one, react so much more quickly than an alkyl halide that is tertiary? What do you think, Dane?
Like there's more hydrogens and stuff in the way for it to attack the center carbon.
Okay. So not necessarily the hydrogens, but there's more crap in the way. That's a good way to put it, right? So if we think about this, if I have a methyl alkyl halide, is hydrogen large or small? It's kind of small, right? So I've got these little tiny small groups, okay? And I've got my nucleophile, and it's got to come in the back side and kick out the leaving group, right? This nucleophile is going to come into close proximity to those hydrogens, which are small. So the steric crowding, as we call it, is actually pretty small, pretty minimal. But if I think about a tertiary alkyl halide, and I'm going to leave the leaving group the same here, and I'm going to actually draw out the methyl groups a little bit so you can kind of see some three-dimension. Oh, I should have made that. There we go. Now, if I'm a nucleophile and I got to try to come in from the back, what's going to happen? I'm going to start bumping into all this methyl stuff, right? I'm never going to be able to have my lone pair of electrons overlap effectively with the antibonding orbital. It's being shielded, if you will, by those alkyl groups. So SN2 is not possible here because there's just too much crap in the way. Okay? What about secondary? All right, so I've got two alkyl groups, so it's not as crowded, right? Yeah, so it's going to slow it down if it's an SN2 reaction, right? But it's also going to slow down in an SN1 reaction because the carbocation is not going to be as stable, right? So secondary is that kind of that special place where you can have both SN1 and SN2 chemistry occurring. So the take-home message, methyl alkyl halides and primary alkyl halides like to do what? SN2. Tertiary and secondary can do both, right? Very good. So if we think about an SN1 reaction, you need to know these things. These need to be committed to heart. Don't waste your time on your note card with this. You need to know that the kinetics are first order. You need to know that the mechanism is two steps. You need to know that the stereochemistry is either going to be racemization or partial inversion. And you need to know that the more substituted the alkyl halide, the faster the reaction for a given halogen. So if we're talking about alkyl bromides, we know that a primary alkyl bromide essentially doesn't react. A secondary is going to be faster, and a tertiary is going to be faster. Okay? So you need to know those identities. Okay? And of course, the reason has to do with carbocation stability, which we talked about just a few minutes ago. So I won't go over this slide again. Okay? Ignore that slide. Ignore that slide. Ignore that slide. Ignore that slide, because we've already gone over this. So the nucleophile. In these reactions, it's not just the electrophile that's important. The nucleophile also comes into play when we're talking about what kind of reaction. SN2. SN1, the nucleophile doesn't come in at all, right? So when we're talking about nucleophiles, we're generally talking about SN2 reactions. You need to know that nucleophilicity parallels basicity, but it is not identical. Okay? So for example, if we were to compare the nucleophilicity of hydroxide versus acetate, both of these are oxygen nucleophiles. They're both negatively charged. Which one would you predict to be the better nucleophile? Hydroxide or acetate? What do you think, Amber? Which one's going to be a better nucleophile, hydroxide or acetate? Sure you do. If nucleophilicity is parallel, I don't know what I'm trying to say. If it parallels basicity, which one's the stronger base? Hydroxide or acetate? Look at the pKa's. Which one's the stronger base? Hydroxide or acetate? Acetate is the stronger acid. It's hydroxide. Hydroxide is a better base than acetate because water has a pKa of nearly 16 and acetic acid has a pKa of nearly 5, right? So which one would we predict to be the better nucleophile? The hydroxide. So we have a hypothesis. How will we test this hypothesis? We will do a reaction. And what kind of reaction will we do? Okay, we need to do some type of SN2 reaction. Tell me some more. That's not enough to answer the hypothesis. Our hypothesis is that hydroxide is a better nucleophile than acetate because hydroxide is a better base. And you need to test that hypothesis and either prove or disprove it. Right? Well, disprove it. How do we need to proceed? If I want to run an SN2 reaction, what would favor an SN2? No.
Oh, no, sorry, methyl.
I want methyl, right? Okay. So I would want either primary. I could use secondary, right? Secondary can do SN2, but tertiary I would not use at all, right? So we'll set up a reaction and measure what? The speed of what? What do you mean by that? Okay.
You measure the rate, whichever one with the hydroxide or the acetate, whichever one goes faster, the nucleophile react better, correct?
All right, that's true. How will I actually do this experiment? You make it sound real easy.
You have to analyze
Okay, analyze the products and what are these products going to be? What functional group are the products going to have? If I take hydroxide and react with an alkyl halide, what will my product be? Be an alcohol, right? So I have to have some way of measuring how much alcohol I'm generating. And if the acetate reacts, what's my product? It's an ester, so I have to have some way of measuring the quantity of ester that I have formed, right? So how do I do that? with the second lab? How are we going to figure it out? Are we going to run the reaction separate? We could, but there's an easier way to do this. I could, and this is called a competition experiment. And for all of you that are in polymers, this is what you do all the time, right? You do competition experiments to figure out the rates of your polymerizations. So basically what we would do is we would start off with an alkyl halide, and I just started off with bromocyclohexane, and I would put in equal moles of sodium hydroxide and equal moles of sodium acetate. And I would let the reaction run. And what I would find is that the major product would be the alcohol, and the minor product would be the ester. The ratio of those products gives me the ratio of the rates. Okay? And so, since these were equal. So what can I conclude from that? What's the better nucleophile? OH, right? And so I just answered my question. I would, and for reasons because you want to make sure that you want to make sure it goes to completion, but you also want to keep in what we call a pseudo first order reaction with respect to the Matthew, Jordan. For those of you who were not at the Ian, who were not at the workshop the other night, you have an opportunity to redo inverted lecture 4 for half your missed points. But you need to turn that in Friday, okay? Friday we will finish up chapter 6 and have some inverted stuff. So see you all on Friday. Pardon?
Is this logic correct? OH negative is smaller than acid.
There is some of that.
But is that not for like all the time?
But not in this particular case, because the acetate we can actually draw resonance structures for, so that negative charge is actually delocalized over multiple atoms, which makes it less basic, which makes it less nucleophilic.
So that's
That's the. But size does matter, and we'll get into that a little bit more